This video is going to look at problems from discussion 6, focusing on reactions of alkenes and alkynes. This question is just reviewing how we use curved arrows to break and form new bonds. To get started, I can see that I no longer have this double bond here. I'm going to use this double bond to go grab the deuterium, push electrons onto the chlorine to make my Cl-. Now at this point, I can see that the carbon-deuterium bond is still there, but there's a hydrogen missing from this position. So we're going to use our chlorine atom to take the hydrogen, and we're going to push the electrons from this carbon-hydrogen bond down in order to make a double bond between these two carbons to get rid of our positive charge. For the bottom one, I see that I have an oxygen and I have a hydrogen added. So I'm going to use one of the lone pairs to grab this H, push electrons onto the chlorine. Now this part, you should be able to see that we're going to need to make a new bond from the chlorine to this position, and that's going to end up having the OH group on this position. This is very similar to what we're doing in this video with the bromonium ion, right? So our Br- or our water will come in, add to this position, push electrons out onto the bromine. And so here's an example that we changed the three-membered ring a little bit, and we changed our nucleophile, but same idea with how we're going to draw our curved arrows. So my Cl- will come in, attack at this position, we'll break the carbon-oxygen bond, and that'll end up putting the OH on this carbon and the chlorine on this carbon. For this top reaction, we know that this is going to follow Markovnikov's rule, so our hydrogen is going to end up on the position with more hydrogens. That means we're going to form our carbocation here. This would end up being a secondary carbocation, but we have potential groups on the position next door in order to make the more substituted carbocation. So this one's going to involve a methyl shift. We're going to move one of these methyl groups over to this position, which ends up making a tertiary carbocation on this carbon, and that's where the chlorine is going to end up. For our next one here, this is acid catalyzed hydration of alkenes. We're going to end up adding a hydrogen again to the less substituted position. Water is going to come in, attack the carbocation at the more substituted position, and then we're going to use another water molecule to deprotonate, and so we'll end up with our alcohol. For the bottom one, this is our alkyne hydrogenation. Notice we're using the Lindlar catalyst here, so we're going to end up seeing this stop at the alkene, specifically the cis-alkene. So you don't need to draw these H's like this. I added them here to make sure that in your drawing you should be able to clearly see you are drawing your Z or your cis-alkene. This question is very similar to the reaction we just talked about with the hydration of alkenes. And so let's go ahead and use our acid in the exact same way to get things started. So at this point, let's go ahead and draw out our H3O+. We're going to have our alkene go out and grab our hydrogen and push electrons onto the oxygen. So we know that the hydrogen is going to end up going to the position with more H's. This carbon has one H, this carbon has no H's. So we're going to end up forming our carbocation here, and we'll also make water as a result. Now at this point, I could use the water as a nucleophile, or I have lone pairs on this oxygen. And this is where I might look at my product in order to see if I can recognize any specific carbons in my product versus the intermediate I just made. So I'm going to number these carbons, and I notice that carbon 1 is the carbon that's connected to two methyl groups. And so that immediately tells me that this must be carbon 1 because it's the only carbon that's connected to two different methyl groups. Now if I keep going, 1 is bonded to the two methyl groups. That means this must be carbon 2, must be 3, and this must be 4. And so if I use water, there's no way I'm going to be able to get my oxygen to be bonded to carbons 1 and 4, but this oxygen is already connected to 4 and has lone pairs. So we're going to do an intramolecular reaction where the lone pairs from this oxygen are going to come in and attack carbon 1. That's going to give me my 5-membered ring. Now notice the oxygen has the hydrogen on it, so it's still going to have the hydrogen in the next step. And now in order to turn this into my final product, I can go ahead and label my carbons again if I want. I'm going to use the water to remove this hydrogen, push electrons onto the oxygen, to get my product. I also can see this is only a catalytic amount of H3O+, so I should regenerate H3O+ at the end. Now that we've covered all the reactions from chapter 4 and 5, I want to show you different ways I can ask questions about them. So in question 2, we looked at providing products. This question is going to look at providing reagents to complete these following reactions. So you should be going through your catalog and trying to pick which one is going to help you get these products. For the first one, I can see here that I have an alkene, and the 2 carbons that were connected in the alkene are no longer connected in my products. So I should be thinking about ozonolysis here. I also can tell that I have a ketone and a carboxylic acid as a product. This carbon here has a hydrogen. So if I had dimethyl sulfide as my second step, I would end up with this as an aldehyde. Since this is a carboxylic acid, we're going to end up using our H2O2 with water as our second step. For the bottom one, I'm thinking about what reaction is going to turn an alkyne into a ketone. So the other thing I would think about here is notice that the double bond oxygen has been added to the more substituted position. And so I'm going to want to end up using something that follows Markovnikov's rule. That's going to eliminate using my hydroboration reaction here. So if we want to turn an alkyne into a ketone, we're going to end up using our mercury catalyst with acid and water. And that'll end up turning the double bond on this carbon here. I can also ask questions where you're asked to provide the starting materials. Now, what's nice about this type of question right now is that in chapter 4, we've really only discussed reactions involving alkenes and alkynes. So really, I'm trying to figure out what types of alkenes or alkynes I need in these boxes, and the reagent conditions can kind of help me. Now, HBr, that as a reaction we talked about as being able to happen with alkenes or alkynes. But if I only see one bromine here, that means that it needs to be from the alkene. I can have the double bond going in either direction. In either way, this is going to end up being the more substituted position, and that's where the bromine is going to add. For this next one, recognizing that these conditions are our oxymercuration reduction. These are conditions for an alkene reaction, and so now I'm trying to make sure that I draw an alkene where this carbon is either the most substituted carbon or tied for the most substituted carbon. And so in this case, I can make my double bond go into the left or the right. That's going to end up being the same. This wouldn't be a great yield because I'm going to end up having the same type of carbon in both cases. So I have a secondary and a secondary. I would have the OH add here and here, but this is the only alkene I can use in order to make this even half of the time. The other part with this question is recognize that the way I've drawn this is my E isomer. So I can see that I have an H pointing up here and H pointing down here. So this would also be able to be labeled as trans. If trans is a possible answer, I also can draw the same alkene as the cis isomer. My next one here, I'm seeing Br2 with H2O as a solvent. This should also be identified as an alkene reaction. So now I'm trying to figure out where would I add the alkene in my molecule that's going to end up having the OH add to this carbon and the bromine add to this carbon. For the mechanism for this, remember that water adds to the more substituted position. So I'd want this carbon to be the more substituted position in my alkene and this carbon to be the less substituted. So the other answers I saw would end up having the double bond be in this position or this position, but that's not going to have the bromine go in the right spot. So my double bond should end up being out towards this CH2 group. Now my water can add here, my bromine can add here. Here are some more predict products questions. So here's an example where we can use HBr to react with an alkyne. Notice there's excess HBr, so I can add more than one equivalent of HBr if I have an alkyne. This is still going to follow Markovnikov's addition, and that means that the most substituted carbon in my alkyne is going to end up getting both of the bromine atoms. So this carbon here has a triple bond and no H's. It's now going to have two bromines, This carbon has one H, it's going to end up picking the two H's from the two HBr molecules. This next one is our hydroboration oxidation reaction. We should be able to classify this as an anti-Markovnikov addition. That's going to end up forming an alcohol. That means my alcohol is going to form on the less substituted carbon, so my OH would end up forming here. Here's another example of ozonolysis. So we are going to go ahead and cut this double bond. Notice in this case, the carbons are still going to be connected to each other, so I'm not going to have two products. Step 2 is my dimethyl sulfide. So once I cut this double bond, add an oxygen to each carbon, I'm set. So you'll end up having something that looks like this. So we're going to end up taking the two bonds for this carbon, adding an oxygen, break the two bonds from this carbon, add an oxygen. You can also redraw that as a linear form if you want to be able to see that better. But so if I counted my carbons, this would be carbon 1, 2, 3, 4, 5, 6. Here is 1, 2, 3, 4, 5, 6. This last one is going through the curved arrow mechanism for part 1 of the oxymercuration reaction. And so what I wanted to see were curved arrows that can end up getting us to this product. In order to get to the final product for step 2, those mechanism arrows were not covered in lecture. So you should be able to draw arrows to get to this product, but not curved arrows to get to our final product. To get started, we're going to use our alkene to go ahead and make a new bond to the mercury. That's going to end up pushing out electrons onto the oxygen. This is going to go through our three-membered ring intermediate, where our Hg is going to end up having a positive charge. Now at this point, water is our solvent. Water is going to come in and attack the more substituted position, push electrons onto the mercury atom. Now I had water that was neutral. That means when I added a new bond, it's going to have a positive charge. And at this point, you could use your acetate ion here, or you could use another molecule of water, whatever works. But let's go ahead and remove that hydrogen, push electrons onto the oxygen, and that gives us the product at the end of step 1. For step 2, this is going to end up removing this CHG bond and add a CH bond. So this carbon has 2 H's. It's now going to end up having 3. And this will allow us to add an OH group to the more substituted position without the complication of going through a carbocation intermediate.